Okay, Roberto, you think we should start?
Yeah, please, go ahead.
Okay.
We're right on time.
You're right on time. Okay. So welcome to the second session of today. And so we start with an invited talk by Laura Pentericci. And she will tell us about probing reionization and galaxy formation with the most distant galaxies. So if you have questions, either raise your hand or put them in the chat or the Q&A. And go ahead, Laura.
Okay, thank you. I hope you see my screen. And first of all, well, good afternoon and good morning to everybody. And thanks to the organizer for inviting me to give this call. So today I will talk about how we can explore the end of reionization epoch with the high redshift galaxies. We've seen, I think everybody has seen one of these figures. So we've seen actually one earlier this afternoon. This is how we figure out that reionization happens. So we know that after recombination, the universe was completely neutral. And then in the so-called dark ages, the first stars started to form and they started to ionize their surrounding by emitting ionizing photons. And then as time went by, the first largest structure, so the galaxies and the quasars formed, and then they, of course, produce increasingly larger amount of ionizing photons. So the regions around them started to be completely ionized, and then these bubbles eventually overlapped. And the IGM was completely ionized again at time around 1 gigayear after the Big Bang. So we know more or less quite well when this process finished, but we have still a lot of questions on when this process actually started and how it proceeded in time, whether it was a very fast transition or a more slow transition, and also how it proceeded in terms of space, whether it was a homogeneous transition or maybe regions at one given time, regions in the universe, different regions had a completely different state. So the key questions, as said, are again, when did cosmic ionization occur, how it proceeded in time and space, and of course, which were the sources responsible for this transition, so which were the sources that emitted most of the ionizing photons. So I will show today results from deep spectroscopic observations of early galaxies, and we'll give some overview of what's coming next, not just JWST, but also with MOONS, PFS, and SKA. The first question is, of course, when did this process occur and how it proceeded in time? So our current knowledge essentially comes now from two classes of probe. One is a kind of global probe. So these are constraints that we can derive from the cosmic microwave background observations. So in the form of the Thomson scattering optical depth. These results tell us just, for example, that the midpoint of reionization was redshift. These are the latest results from the Planck collaborations. They've been changing a little bit, but more or less they tell us that the midpoint of reionization was redshift 7.7. So reionization happened relatively fast compared to what we thought until a few years ago, and late. The other kind of probe, which is the one I will talk about today, comes from actually observation of galaxies, quasars, and GRBs. And these objects allow us to measure a different thing. So they allow us to measure the neutral hydrogen content of the IGM at a given redshift and for a given line of sight or for a given area. So these are more, say, individual probes. And of course, they don't tell us about the global history. And to reconstruct the global history, so to reconstruct the reionization timeline, we have to make observations at very many different redshifts, and of course along different line of sight, as I will show. And I will concentrate, of course, mostly on galaxies, but quasars and GRBs are also very powerful probe of reionization. For galaxies, but also for quasars, the Lyman-alpha emission is actually one of the most powerful to study, to find galaxies and to study reionization. I will just briefly introduce this powerful tool because we will use it in the following talk, and because it's also very important to, as we've seen in the talks before mine, to measure the redshift to find galaxies at distance that are very distant. So the Lyman-alpha line is primarily emitted by young massive stars and AGN, We know that shock heating, cold accretion, and other mechanisms can also contribute, but mostly it's these two mechanisms. And so in star-forming galaxies, we know that if you have a young dust-free stellar population, a lot of the light can emerge as Lyman-alpha. But Lyman-alpha is a very difficult line to model. So it would take another talk to really explain how the radiative transfer of Lyman-alpha, how the transfer of Lyman-alpha within a galaxy is done. But we know that photons, Lyman-alpha photons, can be resonantly scattered and absorbed. So for example, the presence of a little bit of dust, or the gas kinematic, or the neutral hydrogen coin density in the galaxy can all shape the Lyman-alpha. And so in galaxy, normal star-forming galaxies, for example, redshift 2, 3, we don't see Lyman-alpha all the time. So as you can see here, these are galaxy at redshift, I think around 3. These are restream spectra. In some galaxies, you see Lyman-alpha very bright. In some other galaxies, you see a little bit of Lyman-alpha, and in some other galaxies, you have Lyman-alpha in absorption. So the observed line shape really depends on many different factors. But one thing that we observed back 10 years ago is that as we move to earlier redshift, so from redshift say 2 to 5, 6, the number of galaxies, of star-forming galaxies that showed Lyman-alpha in emission was increasing. So at redshift say 2, maybe only 10, 15% of galaxies showed Lyman-alpha. But as we go to redshift 5 and 6, this fraction actually increased considerably. And for this reason, Lyman-alpha was used increasingly to actually determine the redshift, the spectroscopic redshift of objects. Also because at redshift 4, 5, 6, Lyman-alpha is observed, is a UV line, but is observed in the optical, so in a very nice wavelength range for optical observations. How do we explain this? Well, this can easily, expected in some way, because as you go to earlier epochs, galaxies are probably younger, so they emit more Lyman-alpha. They have more young stars that emit Lyman-alpha, and they probably are also less dusty. So there is less chance that the Lyman-alpha is absorbed by dust. And we know that dust can absorb Lyman-alpha. And actually here is a figure below from the review by Masami Uchi in 2020, which shows that many of the most distant galaxies, at redshift about 7, that are known today have been confirmed through Lyman-alpha emission. We start to have a few galaxies that are confirmed through, for example, ALMA observations, but still Lyman-alpha is our best tool to confirm the redshift of the galaxies. The Lyman-alpha emission is also a powerful probe, not just of the galaxies themselves, but also of their surroundings, and precisely of the IgM that surrounds the galaxy. Indeed, as we enter in an epoch where the IgM is not completely ionized, which happens at some redshift, we know that at some redshift, galaxies will start to be in regions of the universe which are not ionized, completely ionized, but which contain some neutral gas with varying fraction. So as we enter in this epoch, the galaxy, the Lyman-alpha photons that escape the galaxy and the CGM of the galaxy, the ICM and the CGM, start to be actually suppressed by the neutral hydrogen gas. So in this figure, we see that, for example, if you have a Lyman-alpha galaxy that is surrounded by completely neutral IgM, its light will not be transmitted. So even if the galaxy itself has Lyman-alpha production, we will not see it. Whereas if you have a galaxy which is sitting in an area of which is already ionized, its light will be transmitted to us. So the Lyman-alpha visibility is actually depends on the amount and the distribution of the neutral hydrogen in the intervening IgM. Okay, not just Lyman-alpha visibility, so the number of Lyman-alpha emitters we see, but also, for example, the clustering of Lyman-alpha emitting galaxies will depend on the distribution of the neutral hydrogen in the IgM. So, for example, here to the right, you see 3 panels. So in the above one, you have these are simulations. Of course, you have a distribution of neutral hydrogen contact in a patch of the universe, and in the the figure below, in the panel below, you see the Lyman-alpha emitter distribution. So you see that there is really an anticorrelation. So in the patches which are still completely neutral, you will not see Lyman-alpha emitters, of course, because the light in these regions cannot travel. Whereas where in the parts of the sky where of this region of the universe where the IgM is almost completely ionized, you will see Lyman-alpha emitters. So the clustering of Lyman-alpha emitting galaxies will also depend on the IgM conditions. And finally, also the Lyman-alpha profile will depend on the IgM conditions. So these three things we can all study in galaxies. And these are three different probes independent also that we can study. The effect on the neutral IgM content on the Lyman-alpha visibility can also measure in two different ways. Well, first, one technique that many people have devised is to measure the differential evolution of the Lyman-alpha and the UV luminosity function. So the Lyman-alpha luminosity function basically counts the number of Lyman-alpha emitters that you have at some redshift, whereas the UV luminosity function counts the number of UV selected galaxies that you have at the same redshift. Of course, the first one, so the UV luminosity function and the UV luminosity density will depend on many different things. For example, the star formation evolution, the galaxy evolution. So all these various things, these very physical processes that come to shape the luminosity function in the UV. The evolution of the Lyman-alpha luminosity function will depend on the very same physical processes, so on galaxy evolution, on the star formation rate, density, and so forth, but also on the IgM neutral fraction. And so the two will be coupled basically when until the point when the IgM is completely ionized. So for example, up to redshift, in this case, up to redshift 6.5, the two will be coupled. There will be, of course, a shift between the two in the sense that we know that not all galaxies emit Lyman-alpha, but their evolution in redshift will be coupled. But there's a certain point, what we observe actually is that whereas the evolution of the UV luminosity density, the blue line here, is mildly going down, the Lyman-alpha luminosity density actually has a complete and abrupt lowering. So at this point, at redshift, say around between 6 and 7, we have kind of this decoupling, and the Lyman-alpha luminosity density goes down much more than the UV luminosity density. This has been interpreted as a sign that at this redshift, the IgM starts to become neutral, and so plays a role in this quantity, in the determination of these quantities. Another very similar and complementary technique is actually just to count the fraction of UV selected galaxies that have Lyman-alpha in emission. And this basically is it is a technique that many people are using. So basically what you do is you observe your UV selected galaxies, you try to determine the fraction of galaxies that have Lyman-alpha above some threshold, of course, some flux or equivalent with threshold. And what we've seen is that, as I say, there is a rapid rise until redshift 6, and this is due to the physical processes that I was talking about before, so less dust, younger population. But then at redshift above 6, you have again a rapid fall of Lyman-alpha fraction. So at redshift 7 and redshift 8, basically the number of galaxies UV selected, so they're exactly the same galaxies in terms of UV properties, but they don't show Lyman-alpha anymore. And this again has been taken as a sign of the fact that the IgM starts to become neutral above redshift 6. So now, of course, the question is how exactly and when exactly does this happen and how it proceeds in time. So the earlier results of many different groups have actually tried to determine this, how this fraction varies, also how it depends maybe on the galaxy properties. And because maybe bright and faint Lyman-alpha galaxies reside in different areas, in different regions of the universe. So of course we want to probe the average conditions. The earlier results by many different groups showed a lot of contradictory actually results, also because the early samples, of course, were heterogeneous, were quite small. And also we found immediately that there were large field-to-field variations. So what you normally did was observe one small field, you maybe we're observing 10 or 20 galaxies. And so your results could be very different from other people's results who were looking at another field. And so we immediately realized that probably reionization was not a homogeneous process, but was very patchy. So it was important to probe large areas. So to overcome these problems in the last 10 years, there's been really a lot of large programs that were aiming to observe large number of galaxies and observe Lyman-alpha in these large samples. So this is one effort that we did with our group, and this was a large program carried out with FORCE2 at the VLT, where we observed more than 160 galaxies at redshift between 6 and 7.3. And here you see in the left panel some of the results. These are all Lyman-alpha emission in the highest redshift galaxy we could secure. A similar effort was conducted by our collaborator, Finkelstein, Jung, and collaborators with Keck, with Deimos and MOSFIRE. With MOSFIRE, you can also probe Lyman-alpha at redshift above 7 and arrive at redshift 8 because it's a near infrared spectrum. Again, here is an example of a redshift 7.6 galaxy. You see how faint these features are. The Lyman-alpha is actually quite faint. These are all observations that are maybe 10 hours integration on a 10-meter telescope. And in a complementary effort, the group by Maruza Badlakov, which I also collaborate, actually try to exploit the magnification power of lensing cluster to reach galaxies with much fainter MUV. So instead of just going in a random field and select candidate redshift 6 and 7 galaxies, in this case, what we did, we selected galaxies behind lensing cluster, and so we could determine the redshift and the Lyman-alpha properties of galaxies as faint as MUV minus 16 in some of these in this cluster. And I don't have time, of course, to talk about all the different programs, but there's been really a lot, and this is really an incomplete list of programs. So just to show how hard are these observations, this was a candidate that many different groups selected. It's a perfect redshift 7 galaxy from ultra-deep HST imaging, and different groups went to spectroscopically confirm its redshift. And so we could gather 52 hours of FORCE2 time of VLT exactly on the same objects, but we don't see any Lyman-alpha. So this galaxy either doesn't have any intrinsic Lyman-alpha production, or it sits in a very neutral region in the universe, and so its Lyman-alpha cannot travel to us. So of course, the next step is to convert the measured transmission of Lyman-alpha to a constraint in the IgM neutralizing fraction. So basically to go from the left plot, which is the Lyman-alpha fraction versus redshift, this is a compendium of the latest observations, to a neutral hydrogen fraction in the IgM versus redshift. This is really a non-trivial exercise. It requires really a lot of modeling of the physics from parsec to gigaparsec scales. I don't have really time to go into many details, but you really need large-scale cosmological simulations to produce the maps of cosmic ionized neutron and ionized gas, and then you have to resolve the self-shielding clumps that are near the high redshift galaxies, and finally you have to do the radiative transfer, the emission and transport of Lyman-alpha photons through the ISM, the CGM, and then through the IgM. And so what you normally do, basically, there are a lot of models that have been carried out and been developed by the different group. What you basically in the end do is you predict a distribution of Lyman-alpha emission, equivalent with distribution or flux distribution of Lyman-alpha in the galaxies. So this is the intrinsic production after the CGM transition, and then after the passing through the IgM. And then what you do is you compare this predicted distribution to the observed one, and you try to infer the best neutral hydrogen fraction that fits the data or that reproduce the data. One important thing is that there are many degeneracies. For example, just show one example here. The effects of small scale H1 absorbers can mimic very much the effect of a diffuse neutral IgM. So for example, here is a model by Kakiji et al. And they have a bubble model in which the small scale H1 absorbers are neglected, and the web model in which they only consider the H1 absorbers. And so they look completely different, but basically panels in the same column give a similar suppression of the Lyman-alpha visibility. So you would produce with completely different IgM neutral gas distribution, you would produce similar suppression of the Lyman-alpha visibility. So you really have to make a joint analysis of many different constraints to discriminate between models. The current results are here, and well, it's not very encouraging in some sense, because in this figure by Wald et al., you see results not just from the Lyman-alpha emitting fraction and LBGs, but also from the clustering analysis and the QSO dumping wing and other probes. And you see that these are the colored areas. The error bars are still really large. The three lines here are three cosmic reionization history. A gradual reionization scenario, it's the full line. The dashed curve is a late and rapid reionization scenario, and the dotted line is yet another scenario. You see that maybe we can rule out the gradual reionization scenario, but the details are really still uncertain. So we really need to, of course, put down the error bars of our probes. And how do we do this? Well, of course, JWST will really help us here, because we will be able to routinely observe Lyman-alpha down to very, very faint fluxes. But not only this, JWST will be able to determine redshift, precise redshift also of those galaxies that don't show Lyman-alpha, because we can have access to the other lines, so, for example, carbon-3 or oxygen-2. And these lines don't suffer from the neutral hydrogen absorption. So we will really be able to determine this fraction of emitters very precisely. This is a simulated spectra of a redshift 8.9 galaxy from the ERS programs CHEERS by Steve Finkelstein, which shows how we can, in a few hours, really detect all the UV Lyman-alpha and the other UV and optical emission lines. In parallel to this question of solving the reionization timeline, we are trying to address another very interesting topic, which is the topology of reionization. We can already maybe say something about this in present data. Here is a very simplified picture of what we mean by smooth reionization versus patchy reionization. So basically, if you have an intrinsic distribution of Lyman-alpha, the central panel, if your reionization is a smooth transition, of course, all regions more or less will have the same transmission, and for example, clustering is unaltered. Whereas in a patchy reionization, some regions will have a much higher transmission than others. We already know that results favor the patchy reionization scenario, so this transition was not smooth. What can we say at the moment is that we are starting to find the first very significant regions where ionization started early. We call them bubbles of reionization. And we're starting to find quite a few of them. So this was the first one that we found in one of our earlier programs. And in this region, we discovered 3 bright Lyman-alpha emitters at basically the same, almost the same redshift, and within a region of less than 2 proper megaparsecs. So very, very close to each other. Actually, 2 of them are even at 19 kiloparsec from each other. So in this region, what we can do with these galaxies, we can estimate the size of the ionized bubble that each galaxy can carve by itself. And this will depend, of course, on how many ionizing photons the galaxy is producing, how many of these photons can escape to the IgM, and of course, how long this activity has been going on, so the star formation activity. What we found in this case is that the 3 emitters cannot carve a large ionized bubble large enough to allow the Lyman-alpha to escape, okay? So unless they have a very high and very unlikely escape fraction. So if we just take their properties there, for example, the number of ionizing photons that they're producing, and we take normal value of escape fraction, for example, 10% escape fraction, here in this figure, you can see that there's no way they can produce, even if they put them together, we sum their contribution there, they cannot get to this 1 megaparsec bubble size that is the one that is needed to allow the Lyman-alpha to escape. So why do we see them? Well, probably in this case, we see them because we see there is an overdensity of galaxies. These 3 emitters actually sit very close to another 14 Lyman break galaxies, so galaxies with photometric redshift around 7, but for which we don't have spectroscopic redshift yet. So if you just produce a luminosity function, this field is 4 times overdense compared to the normal field. So these companion galaxies, we think that they are the same redshift. We haven't been able to confirm their redshift yet, but if they are the same redshift, and if you actually sum their contribution in this equation, so also their photon production and escape, they can actually have helped form this bubble. So this is an example of what we call ionized bubbles, but there's been actually few more in the literature. So this was a very nice example, and it's even nicer because it's at redshift 7.7. This is just 600 millimeters after the Big Bang. Okay. And in this case, what the authors found is that the brighter galaxy is a triplet of galaxies, but in this case, the brighter galaxy had properties such that it could produce an ionized bubble large enough to allow the other 2 galaxies to have their Lyman-alpha photon transmitted. So in this case, it's a combination again of the 3 sources that allow the Lyman-alpha to be visible. And in the last months, there have been more examples. This is on even larger scale. For example, this is an overdensity identified with 16 spectroscopically confirmed galaxies, and these are overdensities on large scales. We're talking about some tens of moving megaparsec. And another example just came out is in the cosmos field at redshift 6.8. So in all these cases, what we observe is that there are more galaxies, there are overdensity of galaxies, and this is what can basically allow the Lyman-alpha photons from also the fainter galaxies to be seen. Constraint on the topology of reionization and sizes of H2 regions will come, of course, from studies on much larger scale. So what we need to really determine is the spatial distribution of Lyman-alpha emitters on scales that are really larger than the small fields that we are now analyzing so far. And the first large program that is addressing this is Silver Rush, is the Subaru strategic program that is mapping the distribution of Lyman-alpha emitters on larger scale. But for the future, we have 2 more instruments that will be really giving us a great advance in this field, and these are MOONS at the VLT and PFS on Subaru. And the reason is that these instruments will cover also the near infrared, not just optical, and so they will allow us to also find Lyman-alpha emitters at a redshift greater than 7, so when the Lyman-alpha shifts in the near infrared. In particular, here I have a presentation of MOONS that will operate in visible and in infrared, and we'll have a field of view of basically 500 square minutes. So we're really talking about large fields of view, and we will be able to observe up to 1,000 galaxies at the same time. So these instruments will really give us capabilities that are complementary to NIRSpec. NIRSpec is really a great instrument, but of course it has a very small field of view, and so it will not be able to map the large scale distribution of Lyman-alpha emitters. But instruments such as MOONS and PFS will be able to do this. So it's really great that we have all these facilities coming online. And of course, in the even further, we have powerful synergies with SKA. SKA will really provide constraint on the neutral hydrogen fraction, and so SKA will be able to map the 21 centimeter signal, and by cross-correlating the SKA signal with the Lyman-alpha distribution map, we'll really be able to constrain reionization models. So all this is very nice, but we are left with the last question. Well, we are left actually with many questions, but of course, one thing that I didn't mention at all is what are the culprits? So we are talking about reionization, how it proceeded in space, time, and so on. But of course, another very important question is which galaxies, which sources were the galaxies or AGN, which sources provided the ionizing photons? So the ionization rate is depends on these three parameters. So the UV luminosity density, so how many galaxies we have, the production of ionizing photons, but also the escape. And we have still no idea on, especially on the escape fraction parameter. But of course, this would require another talk. So I leave with my conclusion. So despite the hard efforts of many groups, the end of reionization is still a large enigmatic period in universe history. So we have developed models and observational techniques. So we have, I think, laid out the foundation for a rapid progress in the field, but we really need the new facilities to put an end, well, at least to try to constrain much better our knowledge on the process. And I'll stop here.
Thank you, Laura. Very, very nice talk. Looks like we still have a lot of work to do. So please post your questions in the Q&A box, and we already have one from Christian Meyer. Very nice talk, Laura. How reliable is the identification of Lyman-alpha emission at very high redshifts regarding contamination and mix-up with the O2 line at 3700 of galaxies in lower redshift?
Okay,
because
so in most cases, we actually have the asymmetry of the Lyman-alpha that really tells you that this is Lyman-alpha and not another line. Of course, when once we hit reionization, we know that this can change. So we actually, models expect that if you have a Lyman-alpha which is emitted in a big ionized bubble, and in a big ionized bubble, actually the shape of this line might change. So one thing that will be important, for example, and this with JWST will be absolutely possible, is that because we have such a large wavelength range, if it was another line, we would detect, for example, if it was oxygen 2, you would detect oxygen 3. And so you can, in most cases, you have a wavelength range enough. And for sure, with JWST, we will have a range that is that allows you really to veto the other identifications. Plus, of course, in many cases, I mean, the photometric redshift really is a very good indication of the galaxy redshift. Not only, I mean, not always, of course.
Mm. So a follow-up of that is obviously that the ratio of the O2 lines is changing, right? So you could have like if you have a low resolution spectrum, you could mimic basically a different
resolution. Yes, but for example, moons will have a resolution of 4000. So you will, that's something that you have to take into account, of course. Yeah.
Good. More questions for Laura? You can still think about it. Then I have a question. So what about ALMA? So we detect a lot of galaxies, right, that have ALMA emission, but they don't have anything else, right? So they are super dusty. Is that changing somehow the picture that you painted with the Lyman-alpha fraction?
Yeah, so we, of course, ALMA is a completely new word in the sense that we really started to see all these ALMA detected galaxies without a Lyman-alpha preselection just in the last couple of years. And I think this will tell us a lot about the properties. I mean, we might come up with a modified picture of many things because of ALMA. ALMA also can tell us of close pairs, for example, which of course is something that so far we haven't been able to do with these Lyman-alpha observations. So yeah, I think well, I think that some of the galaxies that showed, well, some of the C+, the galaxies that were detected in C+, were then subsequently followed up in Lyman-alpha, and some of them actually also had Lyman-alpha. But yeah, I think once we have a bit more statistics, I think we will have to rethink a bit our model of the typical, high redshift galaxy. So some of them might be more dusty than what we think. Yeah.
Then we have another question by Roberta Assef. What upcoming facilities do you think will have the greatest impact in answering these questions? I think he's referring to the last, probably the last slide.
So I think, well, I'm really, okay, so JWST might really be revolutionary in the sense that, you know, we will be able to go at much higher redshift than what we're doing now. But what is really needed, what we learned is that we really need statistics. Mm-hmm. So because of the small field of view, yeah, JWST might be harder for JWST to really build big samples. And to do this, we've seen that we really need many, many galaxies. So I'm actually, yeah, I think moons and PFS will also play a role in this sense, because by observing many hundreds of galaxies on very large scale, they might, you know, might help us in many sense.
Mm-hmm. So what about Euclid? I mean, you don't have the resolution probably spectroscopically, but you have a large sample. Does this kind of offset?
Yeah, I think Euclid is yeah, for very, very high redshift galaxies. So Euclid will be fantastic for bright objects. For quasars will be super, but for you know, faint, these galaxies are really faint. So maybe maybe in the deepest field there will be a chance, but the deepest field will come at the end because they will need to be built up. So it's not something that will be amongst the first science cases addressed by Euclid, I think. Yeah. So, and then by the time we are at the end, I mean, by the time we are there where we build up the deep fields, then, you know, JWST will have been working for several years, and then we will have had moons and things. So it needs to be seen.
Any more questions for Lara? Okay, if not, let's thank Laura again for this very nice talk. And let's go to the next speaker, who is Lena Lenz.
Yes, hello. Just sharing the screen. Can you see all that?
Yeah, looks good.
Okay, perfect. Okay.
So please go ahead.
Yeah, so hi, I'm Lena. I'm a final year PhD student at Imperial College, and I'm working on automated methods to find high redshift quasars. So previously what we would do is for a given source, you could download all the available images in a given survey, extract the database photometry, then define color cuts. And with this color information, you could input that to, for example, Bayesian model comparison, which then gives you a quasar probability. Then you can rank those candidates by their probability and visually inspect only the most likely candidates. And upon the visual inspection, you will find some irrelevant sources. And for the remaining ones, you can do follow-up imaging. And then you can repeat this process over and over again until you only have a few sources left. And then you can do the final classification with spectroscopy. But however, as we know, for the upcoming surveys, there's just so much data coming in. So this will become very inefficient. So what we want to do is to swap these steps by machine learning. So we will still include the Bayesian model comparison, but only as a feature. And otherwise it will just be much more efficient and will require far less visual inspection. So just to summarize, we have this data processing pipeline. So we get rid of any unnecessary images with data processing issues. And we also calculate the photometry on our own. So this is useful for sources where there's no information in a database, so that we still have some photometry information. And then we extract all the features, which I'll come to in a second. So one of them is the Bayesian model comparison, and the other one I'll explain in a second. And then you can pass it to different classifiers. And if you're not a fan of machine learning, because it's not that interpretable, which is fair enough. You can then do manual cuts yourself. So here's the motivation for this other so-called feature. A feature is just an input to a machine learning classifier. And so the first thing is that objects that are far away appear to be stationary. So we can model a quasar as a non-moving object between passbands. And then also because they're outshining their host galaxy, they have this star-like appearance. So we can model them as a point spread function. And then they also have a very distinct spectral energy distribution. So we have a set of 9 quasar SED templates for redshifts between 5.5 and 12. And then for the observed photometry, we can get back the best fit SED. So in total, we have a model of a stationary point source that follows the SED of a quasar. And we tested on a pixel level with the chi-square method. And just briefly with the data set, so we have optical and near-infrared image data from SDSS and UKITS, and we're using a pre-labeled set from Daniel Mortlock and Stephen Warren. So they've been visually inspected and visually labeled, and we're trying to reproduce those results. So here you can see a quasar at redshift around 7, and here you can see the residual with the best fit SED photometry. And as you can see, this is just noise, which is great. So you will have a very low chi-square value for that. And then here, for example, you can see a moving source, which obviously is not a quasar. And here with the subtracted SED photometry, you can see there's a lot of residual, so this will give a very high chi-squared. And just as a side note, you can also see that we are reconstructing all the nearby sources, so that they don't interfere with the photometry of the central source. And then, as I said, we have classifiers. So we're using 3 different classifiers. The first one is not a machine learning one, so that it's very interpretable. And the last one is a random forest, which is a machine learning classifier, not that interpretable. So just to the first one, here you can see the chi-squared, our model of this stationary point source follows the quasar SED, and here the quasar probability based on the Bayesian model comparison. Oh yeah, I should also say that the contaminant populations we include are MLT dwarfs and early type galaxies. And these go quite well together. So for example, here you can have sources that have a very high probability just based on color information alone, but actually they're not point sources or the moving in between bands. So then you will end up here. At the same time, you can have candidates that look like a quasar, but are actually much more likely to be a contaminant, and then you will end up here. And in red, you can see the spectroscopically confirmed quasars. So they all have a high probability and relatively low chi-squared, which is great. And so, for example, in this green region, these are the candidates you could observe further. The decision tree we mostly just use to analyze maybe important features, but also to find thresholds for our manual classifier, and also just to see if it chooses good features or not, but it's otherwise less important. And the random forest is just a collection of decision trees. So you could imagine here, if you had just 3 decision trees and this is your input, then the first trees would give you a cat as an output and the last one a dog. And then by majority voting, you would get a cat, which is correct in this place. And the random forest, it has a much better performance, a much better accuracy, but obviously the disadvantage is that you would have to retrain it for every new survey. Okay, and so now for the results. The performance we use is the so-called ROC curve. So you have the false positive rate versus the true positive rate. And then there's so-called AUX score, which is just the area under that curve. So a random classifier would give you a score of 0.5, and a perfect classifier would give you a score of 1, which would be along the axis here. So as you can see here, the random forest gives the best results, but also the decision tree is actually quite good as well for the fact that it's so simple. And this is just the overall result with 10-fold cross-validation. So again, the random forest gives the best results overall. And then we also tested with these redshift independent features or survey independent features as well, if you want, like the chi-square and quasi probability. And still the random forest gives the best results, but obviously not as good as if you include every feature, as like the photometry. And here's also our manual classifier, which is also relatively good, given that it's just so few features. And yeah, we're looking forward to applying this on Euclid and LSST. Thank you.
Thank you, Lena. Very interesting. Any questions? Oh, yes. Okay. So we have a question from JT Schindler. Hi, Lena. Great talk. Very interesting work. Could you briefly comment again on your quasar training set and how it covers the range of different quasar spectral appearances? So, for example, strong versus weak emission, BALs, strong velocity shifts, etc. Thank you.
Yes, so again, it was a pre-labeled set. So they've done color cuts on them. And so, for example, with the redshift range, they're mostly about redshift 6. And there's not that many samples with higher redshift. So in this sample set, for example, this was where the redshift 7 candidate by Mortlock was discovered. So this is one of the highest redshift sources we have in there, and it's not a very uniform distribution or not very representative distribution, I have to say. But for example, for the random forest, there's also this issue with that most of them are not quasars. So we only have 14 actually confirmed quasars in this, and only 800 positive labels. So what we also have to do is to weight, put different weights on them, because otherwise you could just classify everything as non-quasar and you would get a high accuracy. So those are things you would have to take into account as well. And yeah, I'm not sure if I answered the question, but if you would take, for example, the manual classifier, it doesn't matter as much if it's representative or not, because this should apply to basically every data set you get. Does this answer the question?
We have another one by Isan asking, do you tune the threshold for the rock analysis to get the best result, and what features in observations affect this classification the most?
Yes, so yeah, for the rock analysis, just checking this, can I use my, yeah, so I do tune the thresholds there to where I would get the best results. And for the features, so what I actually use is so-called conditional random forest, because many of the feature importance measures that you see nowadays are actually quite biased, whereas this one is not. It's based on conditional probabilities. And you can see here, so I know I haven't explained those with the tilde. It's basically the maximum chi-squared maximum is the maximum chi-squared in one band, because we have the sub chi-squared in every band, and then we take the average of all of them. And so the ones with the tilde are the ones where I also fit for the source center. And this is useful for comparing it with the ones where I don't do it. So you could, for example, if a source is moved, there would be a drastic difference. And you can see here, these are the most important features. And actually all the chi-squared measures are the most important ones. And here also the flux in Z, because that's just the redshift range that most of the candidates are in. Mm-hmm. Yeah.
Then we have 2 more questions actually. Matthew Temple asks if your method can also identify sources that have some extended galaxy emission. So they are not point sources, basically.
Yes. So actually, I test this pipeline against, I simulate candidates, so I simulate MLT dwarfs and also galaxies. And with this, I use an extended point spread function. And this is something that the code can pick up. So if it's extended, it will give a very, very bad chi-squared.
Okay, and last question by Valentina. Can you give an update on the magnitude information of your population, for example, in J-band, referring to if it's basically how faint you can go with your method?
Yes. So in the J-band, again, when simulating candidates, so it can detect it up to, it was about 10 microchansky, and below that, it gets more difficult, and then it will misclassify sources. So if it's below 10 microchansky, so in the J-band, then yeah, it will start getting confused. But above that, it's fine.
Cool. Thank you.
Okay.
For this nice talk.
Thank you.
Okay, so our next speaker is Valentina D'Odorico.
Can you see my slides?
Perfect, yes.
Okay, so hello to everybody. And I will talk about XQR30, which is a survey of quasar at very high redshift, which is based on a large program of almost 250 hours of observation at the XSHOOTER spectrum of the ISO VLT. So we selected the brighted objects that were known at redshift larger than 5.8 at the time we proposed, of course, the observations. And we ended up with 30 quasars at redshift between 5.8 and 6.6 that we have observed at intermediate resolution and high signal to noise ratio. And this quadrupling, let's say, the sample that was previously known with the same quality, let's say the sample of object with the same quality, the same spectroscopic quality. So, of course, this survey is a multi-purpose survey. We want to carry out several science cases. In particular, within the collaboration, what we want to do is to characterize the second half of the reionization process. And you will see later, you will hear later Sarah Bosman that will talk about this. And there will be also a poster by Sofia Campo. But of course, we are also interested in studying the metal enrichment and the ionization in the early universe, the nature of the first stars, and also the quasars themselves and their environment. And there will be also a poster by Wanqing Cheng later today. So in this presentation, I would like just to present you what is going on within the collaboration in these four fields. So there is a paper that is already published by Yong-Da Zhu, who used a sample of 55 quasars, including the XQR30 targets, to study cosmic reionization with dark gap statistics. Dark gaps are a coherent region in the spectra which are completely absorbed, and that, of course, could be due to neutral hydrogen, which is left before, let's say, the reionization epoch. And what is interesting here is to study statistically this, the presence and the length of these gaps. And an interesting result of this work is that he found two long dark gaps, longer meaning larger than 30 comoving megaparsec, that are persisting down to redshift 5.3. And then what he did was to compare this observable that he defined as F30, that is the fraction of quasar spectra that are showing dark gaps longer than 30 megaparsec with the prediction by simulations. And you will see the result here in the picture here below. So what he can exclude is a model with early reionization, and so an homogeneity that ends, let's say, the early reionization that ends at redshift 6, and for which then we have an homogeneous UV background at redshift lower than 6. While F30 was in agreement, let's say, consistent with the prediction by models of late reionization, where the midpoint of reionization is at redshift 7, or models where you have an early reionization, but you still have a fluctuating UV background at lower redshift. Then there is Rebecca Davis, who is a postdoc at Swinburne, who is working on the metal absorber catalog. She analyzed the XQR30 quasar plus the 12 other quasars with a good quality spectra. And she looked for the important doublets like carbon-4, silicon-4, and magnesium-2, and then associate. She looked for also other lines associated with these systems. So there are more than 800 absorption systems in our 42 quasar spectra that are spanning the redshift range between 2 and 6.5. And for example, here you see the completeness of the carbon-4, for example, detection, which are complete to 80% for column density larger than 30.5. These are all, of course, quantities that will be given in her work. And this work will be, of course, the base work to do then others, to study other statistics of all the metal lines. Then there is Alessio Sodini, who is a master student in Pisa, that instead wanted to look for the chemical signature of population 3 stars at redshift 6, and he did it through the analysis of the damped Lyman-alpha systems, which are identified at this high redshift by the presence of neutral oxygen. And this is an ongoing work. So he found 20 systems at redshift larger than 4.7. And he studied all the chemical abundances. And from the preliminary results, we see that they are in very good agreement with the lower redshift, very metal poor DLAs. So they are not showing, in fact, this signature of population 3 stars. Then moving to instead the study of the properties of quasar themselves. There is the work by Emanuela Bischetti, who is a postdoc in Trieste Observatory, who in fact computed the fraction of XQR30 quasars which are broad absorption lines. What she did was to compare then this fraction with what is found instead at lower redshift, selecting a sample from the Sloan Digital Sky Survey with a very similar, let's say, selection function than XQR30, and finding that this bulk fraction is increasing by a factor of 2.5, going from lower to higher redshift. And furthermore, these broad absorption lines outflows are characterized by much larger velocities at high redshift than with respect to low redshift. So what happens is that at this very high redshift, these BAL outflows are injecting a large amount of energy in the host galaxy, possibly, let's say, stopping the gas accretion onto the black hole and starting the symbiotic evolution of the black hole and the galaxy. Finally, there is of course, last but not least, there is another work on, again, on quasars properties and on the metallicity of the broad line regions by Samuel Lai, who studied the ratio of emission lines, which are sensitive in particular to metallicity. And let's say, two main results are that there is no redshift evolution, in fact, found in the metallicity of the broadline region. So with respect to a sample of redshift from 2 to 5, which is represented by the gray points here in these plots. And also the metallicity are quite large, of the order of 10 solar. But what is found is that there is a strong correlation with the carbon-4 blue shift of of the values of these emission line ratios with the carbon-4 blue shift. So one has to first take this into account in order then to get a proper determination of the metallicity. And so I'm done. Really very brief overview of what's going on in the collaboration. So if you don't want to lose the news, you can have a look at our webpage where we are posting all the new projects and papers. Thank you.
Thank you, Valentina. Very interesting. We have time for maybe one question. Okay, then I have one. So can you talk more about, oh no, wait, we have one. Okay, one from Marie-Laure Martinez. Have you explored a relation with the Eddington ratio in bulk USO and the metallicity?
So not, let's, sorry. So between unfortunately we cannot, so I don't know if she's meaning the metallicity of the broadline region or the metallicity of the derived from the BIL. So the metallicity derived from the BIL cannot be obtained from, no, so the metallicity from the BIL cannot be obtained because the lines are very strong and completely saturated. And the one that we can observe, because of course all the lines that fall in the Lyman-alpha forest are completely absorbed. And the metallicity of the broadline region instead, Samuel is excluding the BAL because of course the lines could be modified by the presence of the BAL. And regarding the Eddington ratio, I don't have it on the top of my mind, but I don't think that Manuela did this this comparison. But thank you for the suggestion. A broadline region, okay. So Samuel excluded the BAL. Now I see that Mary wrote broadline region and metallicity.
Okay, thank you, Valentina.
Thank you.
Very interesting results. Okay, so we have Jorryt as next speaker.
All right, thanks. There we go. Perfect. I want to thank the organizers for allowing me to give this talk. It's been a very interesting conference. I'm learning a lot, especially on high-redshift quasars. So in this talk, I'm going to talk about faint galaxies for change. Some of the introduction, fortunately, has been covered by Laura's nice overview. I'm going to talk about resolving reionization with Lyman-alpha emission. I'm going to focus in particular on the sources of reionization and not really on measuring when it happened. This is work done at ETH in Zurich in collaboration with an international team. I want to particularly highlight contributions from Rohan Naidu in Harvard for this work. So the real fundamental observable around which all this work really evolves is the H1 ionizing emissivity over cosmic time. It's basically it's a similar plot as the cosmic star formation rate density that many of us are used to look at. This shows how many ionizing photons escape from galaxies and quasars as a function of redshift. In this particular model by Valentina in 2020, it's a combination of quasars that are particularly dominant at redshift around 2 at higher redshifts into the epoch of reionization, it's plausible that most of the ionizing photons that form the UV background originated from star-forming galaxies. And what's interesting to remark about the evolution of the ionizing emissivity from star-forming galaxies at redshifts above 3, it's relatively flat from redshift 3 to 8, which is quite different from the star formation rate density of these same galaxies. That implies that the average escape fraction, or in fact, the escape fraction times the number of ionizing photons that are produced, evolves very rapidly by an order of magnitude over this relatively narrow redshift interval. And understanding this evolution is challenging. We have some ideas, but it's very unclear. And in order to understand that evolution, we of course need to understand how the escape fraction of ionizing photons depends on properties of galaxies, such as their mass and their age, dust, and metallicity, and so on. In addition to explaining this overall evolution in the escape fraction, the dependence of the escape fraction on macroscopic properties impacts the timeline and topology of reionization. In faint galaxies drive reionization. It happens more gradually. The bubbles are smaller, and there are more bubbles compared to when bright galaxies do the job. And as I said, the main issue is measuring the escape fraction. It's very challenging observationally because ionizing photons are faint, and there are lots of issues like foreground contaminants. But there are also fundamental issues that I just want to highlight. And that is first that at high redshift, at redshifts around 6, when we would like to measure the escape fraction, it's basically impossible to do that directly because, well, we all know the Lyman-alpha forest and ionizing photons don't really transmit towards us. And even at redshift 2 to 3, when we're still at high redshifts, galaxies on average are still very young, the transmission of ionizing photons through the intergalactic medium is around 50% on average. We can overcome that, but there's significant scatter from source to source. So even if we would observe a field like the Hubble Deep Field in the red stream UV continuum, all that light travels through some foreground gas, and that basically blocks the ionizing flux depending on where you are exactly. And the big problem is you don't know which fraction is blocked. So because of that, it's really hard to disentangle which kind of sources have a high escape fraction and which galaxies have a low escape fraction. There are two approaches to solve this. One is stacking lots of galaxies in independent sidelines. This is challenging, of course. You need a lot of galaxies. You need very deep data. You can also look at low redshift analogs of high redshift galaxies because there are basically no gas between those galaxies and us, or very little gas. There are issues with that as well, because how are you sure that these analogs are actually the same kind of galaxies as the ones that you are interested in? So in my talk, I'm going to argue that there's an indirect way that I think is very promising in tackling this issue, and that's high resolution spectroscopy of the Lyman-alpha emission line from galaxies. In these studies of low redshift analogs, the Lyman-alpha line profile which typically appears as double peak, the profile is very strongly connected to the escape fraction of ionizing photons. This profile is relatively easy to measure in high redshift galaxies, especially easier than measuring Lyman continuum escape directly. And it actually bypasses this stochasticity of your foreground intergalactic medium. So you can really use observation of the Lyman-alpha line to separate which galaxies leak and which galaxies do not leak. A big caveat, of course, is that you can also not do this in the epoch of reionization because Laura showed that neutral gas will basically damp the Lyman-alpha flux as well. But at least from redshift 3 to 6, I think you can probably do this. So in my talk, I'll show some results from a recent effort to try to do this at high redshifts with results published in these two papers on the archive. And I'll just go through them quickly. So this comes from the XSHOOTER Lyman-alpha survey, redshift 2. This is a survey of 35 Lyman-alpha emitters, observed for about 3 to 3.5 hours with XSHOOTER The main strength is that you get a full wavelength coverage from Lyman-alpha all the way to H-alpha. So you get many emission lines that you can measure. The resolution is relatively high, and the signal to noise, especially on Lyman-alpha, is really good. These galaxies are really low mass galaxies, 10 to the 9 on average. We go down to 10 to the 7 even, without lensing. And the star formation rates are relatively normal given their mass. What's really fundamental for this particular application to study Lyman continuum escape are these high resolution Lyman-alpha line profiles. In particular, having systemic redshifts from other lines like oxygen 3 and H-alpha really allows us to see where is the Lyman-alpha flux coming from, what fraction of the Lyman-alpha flux do we actually see from those galaxies.
2 more bits.
Really, all right. So what we did is we used the Lyman-alpha profile to separate leakers from non-leakers, and that allows us to see what kind of galaxy properties are associated to leakage of ionizing photons and whatnot. First, we actually don't see differences between mass, star formation rates, UV luminosity, or UV slopes in these different stacks of galaxies with a high escape fraction or low escape fraction. The escape fractions, we believe, are very different. Our fiducial value is actually 50% for half of the Lyman-alpha emitter at redshift 2. The other half actually has a very low escape fraction. And while this 50% value seems very high, I must say it's actually consistent with independent stacking analyses. And my long talk on YouTube has more details on this. So we see that the optical emission lines are very strong in both samples, even though this high escape fraction is expected to reduce the emission line strengths. Interestingly, I'll show this later, is that we see nebular carbon-4 and helium-2 line emission in the galaxies that have an escape fraction of ionizing photons above 20%, versus non-such emission in the non-leakers. There's interstellar absorption lines that are weaker in the leakers. There's basically no dust in the leakers versus some dust in the non-leakers. And in addition, there is a much higher ionization parameter in the leakers compared to the non-leakers. So you see there's lots of different properties that are different between these stacks, and we just split them by Lyman-alpha line profile. So there's lots of physics going on. Just to show, I think what the main result is that we show that the escape fraction is high in galaxies, which also have a very high ionizing photon production efficiency, which is of course good if you want galaxies to reionize the universe. That's indicated by both the nebular optical lines, H-alpha, O3, but also by carbon-4 and helium-2, which really point towards very massive low metallicity stars that are present in these leakers and not in these non-leakers. We can interpret this with this picture that basically the light from galaxies is dominated by star clusters with different ages or groups of star clusters. If you have very young star clusters, the ionizing photons and the Lyman-alpha photons are basically trapped. If the most massive stars start to evaporate their birth clouds with feedback, the Lyman-alpha photons and the ionizing photons can get out. This process will slowly become more and more challenging because dust is produced and actually the hottest stars stop shining ionizing photons. Eventually, there will be some stabilization phase. And we argue that with the Lyman-alpha selection, we pick up these two phases, and by separating by line profile, we can identify when galaxies are actually, when the ionizing photons escape from galaxies. Again, at redshift 2, where we did this, these galaxies are actually relatively rare. And but at high redshift, that may be different. And I'm not sure how I'm doing with the time.
Well, you're basically now in the question time. Yeah.
All right. So I'll just show this. I'll just show this, and then interested people can look at my long talk. So I just want to point out that the evolution of the emissivity from the star-forming galaxy population, inferred from quasar absorption lines, what the UV background should be, shown in green here. The shape of that evolution is very similar to how the Lyman-alpha luminosity density from galaxies evolves. It's very different from the UV luminosity density. And this really suggests that the Lyman-alpha emitters select the subsample of the galaxy population that are actually the main producers of these ionizing photons. just as just to make people enthusiastic for my long talk, you can then connect Lyman-alpha emitters to the general galaxy population with the two different luminosity functions to infer that how the escape fraction would actually evolve with a redshift and with UV luminosity. I'm just going to leave this slide up for my question time. Thank you.
Cool. Thank you. Okay, we have time for one question. From Roman Maya. Could the C4 and helium-2 lines in the stacks indicate HGN activity in the leakers?
Yeah, in principle, yes, and because these lines come from very high, you need very high ionization photons to produce them. We have like BPT line ratios from the optical lines, and those point towards star formation producing basically dominating the ionization. Also, the equivalent width of those lines is not very high. It's around 1 to 2 angstroms, carbon-4, helium-2. That's quite different from AGN, where they are like 10 to 20 angstroms.
Mm-hmm. Okay, so there are 2 more questions, but maybe you can answer them in Slack later.
Right, thanks.
Okay. Thank you, Jorryt. Very nice. Okay, so the last speaker of this session is Sarah Bosman.
Yes, let me share my slides.
That's good.
Can you see them?
That's perfect, yes.
Yes, thank you for the opportunity to attend this conference. I would like to finish this session by presenting some results on the precision measurements of the IgM that have been enabled by the XQGACT30 sample that Valentina presented a little while ago. Quasar spectra are our best way to measure the IgM at redshifts more than 5, as can be shown by looking at the Lyman-alpha transmission. So here we have the quasars from the XQGACT30 survey. When you can see that their continua are strongly absorbed on the left of the Lyman-alpha line, with some transmission left due to a non-fully neutral IgM in front of them. You can see even by eye that at redshift 5, you still have a lot of this Lyman-alpha transmission. By the time you reach redshift 6, almost all of it is absorbed in Gunn-Peterson troughs. This data set is truly an incredible improvement compared to what we had before, just by the quantity of high quality data that it represents. But it turns out that the most interesting part of this picture is not the mean evolution of the Lyman-alpha line across redshifts more than 5 to 6, but the scatter between sight lines at the same redshift, which you can see even by eye, seems to be quite strong. And actually, it's been known for a little while now that the amount of scatter in transmission from one sight line to the next, so corresponding to uncorrelated parts of the IgM, is too strong to be explained by density fluctuations alone. So it's not compatible with a completely homogeneous ultraviolet background that you expect in the post-reionization IgM. This was shown by George Becker by finding this extremely strong contrast between a completely absorbed sight line and a very transparent one at the same redshift. And the entire distribution of opacities in front of in the Lyman-alpha in the IgM is far too broad compared to expectations from a completely percolated UVB, as is shown here in the blue curve. But now we can do a lot better. We don't have to rely on small samples of high quality data or large samples of poor quality data. We can really have both for the first time. And it turns out that the main limiting factor in doing this kind of analyses in the precision regime was how well we could predict the intrinsic quasar emission before absorption by the IgM. Because of course, when you have full absorption, you cannot just guess where the intrinsic emission used to be. And if we can solve that, then we can answer hopefully some important questions, such as down to what redshift do we see these inhomogeneities, how precisely can we measure that, and when does reionization end from the point of view of the UVB. All right, so to improve our grasp on the continuum reconstruction, we performed a large comparative study at lower redshift. This is a quasar at redshift free from eBOS, where we can see where the true continuum lies. But it turns out that the methods that were used to reconstruct this continuum at high redshift, shown here in the colored curves, had not only a large amount of scatter, but they had a lot of bias that was wavelength dependent and went in the opposite direction from each other in past published results. But by adapting more modern takes on principal component analysis in a log space, we have now developed the first few methods with no bias. And the most recent one is this one that is used in the latest XQA30 paper, where we can get the scatter down to 8%, but what matters is that we now have no bias in reconstructing where those continua are. All right, so now that we have a grasp on our uncertainties, what does the transmission look like at high redshift? This is a plot of the optical depth as a function of redshift in this XQA30 sample, which we augmented with a few high quality quasar spectra from XSHOOTER and ESI as well. And you can see that at redshift 5 to 5.2, the distributions look roughly Gaussian. At least they don't seem to show an extremely large amount of scatter around their means, which are in red. And by the time you get to redshift 5.6, there's a lot of contrast between the very transparent parts of the IGM and very absorbed. And so somewhere in the middle, there is a flaring up, which becomes inconsistent with a completely homogeneous ionization. To showcase the improvement in data quality, this is how well we can measure the mean flux of the Lyman-alpha forest, now in this new sample in red compared to past works in gray. The redshift sampling is a lot finer, and every single error bar on this plot is a bootstrap uncertainty. So that really shows the fact that past samples either had to be high quality and small, or large or larger and lower SNR. And we have also tracked down all disagreements between past studies, between each other and our sample, mostly in the major parts, the continuum reconstruction systematics. And on the right, there's a comparison to the previously larger sample in gray compared to our new results in red. And you can see that they look a lot smoother. We have fixed all the systematics we could find. With higher data quality, we can also exclude DLAs and galactic absorption from the sample a lot more efficiently than before. And the sample is also larger. So the distribution finally start to look smooth and well-behaved, which is great to see. Can we tell at what redshift they start becoming incompatible with a homogeneous universe? Yes, is the answer. We're quite surprised by how well this worked. So we compared our distributions, which are shown in these CDF panels, to the simplest models of the completely percolated UVB that you can come up with, where all scatter is only due to density fluctuations and no extra temperature fluctuations or any UVB effects, shown here in the blue and the yellow crosses. And then we forward modeled the simulations, including all observational characteristics. So we made mock samples of the same size, same SNR, and same continuum reconstruction uncertainties as the data, and so that we could assess the probability of our observations given the entire observational setup with no summary statistics. So just establishing how rare a draw from the simulation would be to look like our data, which is what is shown in these bottom panels. These are the likelihoods of drawn from the simulation, and the observations are in the black line. So as you can see at redshift 5.2, our observations are a completely typical expectation from these homogeneous UVB simulations. But as soon as we get to redshift 5.4, the data is completely excluded from the simulations, which means there is a negligible probability that this would occur by chance in a homogeneous universe. And you can also see this in the CDF panel, where even though it looks like a very small difference, in reality, this is excluded at our sampling limit of 4 sigma. So the transition at the end of reionization is very fast between no need for extra scatter and definite need for extra scatter. Another thing we can do now that now that we trust that the homogeneous UVB models are sufficient up to redshift 5.2, we can trust those models and translate the mean Lyman-alpha transmission values into better measurements of the neutral fraction, which are shown here in black, which is an order of magnitude improvement upon past measurements. Unfortunately, at all redshifts 5.4 and above, because the models of the UVB that were previously used to make this conversion have now been rolled out at a very high confidence, we can no longer measure the neutral fraction and only put limits. It is an important change compared to all the published work. Valentina already presented this other avenue of evidence from Young-Dazu's paper, where he reached a similar conclusion by looking not at the mean optical depths, but at the occurrence rates of these very opaque contiguous troughs of 30 megaparsecs or more. And he found that they also evolved very quickly from redshift 5 to 6. The fraction of sightlines that are currently in one of those dark gaps evolves very strongly. And at redshift 5.3 is when the first such features emerge, which are completely unexpected in a homogeneous UVB model. However, he didn't find any of them up to redshift 5.3. So there seems to be some agreement from both the overall distributions of optical depths and this morphological measurement that reionization ended, so to speak, at 5.3, and inhomogeneities in the UVB persisted until at least 5.4. Why might this be? What extra ingredient do we need to add? Does this mean that reionization is late? Well, we don't have quantitative comparisons yet. They are in prep. But roughly speaking, the main 2 avenues that have been explored are either indeed a very late reionization, where midpoint per volume of reionization at redshift 6.5, which is the slice shown here at the bottom from this paper by Girish Kulkarni. And in this model, the most opaque regions at redshift 5.5 are in fact highly neutral, and they are opaque because they are 10% neutral or more. So it's a very late model of reionization. You can also get a kind of similar effect of a very patchy UVB if you accept that the ionization mean-free path of ionizing photons is very short. Then you can have a midpoint at redshift 7.5 or even 8, if we look at the latest papers on this. But that comes at the price of many more sinks of ionizing photons in the IGM to make the mean-free path so short, which in turn means a very large increase in the requirement of ionizing photons from galaxies. In reality, there is probably a combination of both these explanations, and we are working on systematic ways of constraining these parameters with the data. So in conclusion, the XQR30 sample is really a game changer for Lyman-alpha studies above redshift 5. We can finally do precision IGM measurements. We have also unlocked the potential of these IGM measurements by finally having a reconstruction method with no bias, which is great. And both the distribution of optical depths and the existence of dark gaps point to the same end of inhomogeneities in the UVB at around the redshift of 5.3, between 5.2 and 5.4. And stay tuned for the upcoming quantitative comparisons to models. Thanks.
Thank you, Sarah. Questions? We have time for one short question. question? Your last chance. Oh, yes, okay. Jorryt has one. What would physically be the origin of a short mean-free path?
So it has to be self-shielded systems. So Lyman limit systems. So in other words, the gas has to be very clumpy on small scales. So if you increase the number of Lyman limit systems in the IGM by factors of a few, that will shrink your mean-free path. And there is some evidence that this is in fact the case from George Becker's measurement of a very short mean-free path last year.
Good. Thank you, Sarah, and thank you all the speakers of this session. I think we are having a break now.
Yes, indeed. So thank you very much to all the speakers. Thank you very much, Andreas. And so we'll have a break